guys, I am Su Cheng, and this is my first physics video of the year. I'll be covering 4 topics in this video, namely pressure, uh, moments, resolution of forces, and projectile motion. So I'll start off with pressure. So basically in this video I'll be covering all the Sec 4 non-electricity topics. So I'll start off with the definition of pressure. So pressure is defined as force over area. So here P is pressure, F is force, and A is area. So let me move this here, and let me add a term here. So there are a couple of things you need to know about pressure. First thing you need to know is that pressure is a scalar quantity, not a vector quantity. This is because it has magnitude, no direction. It basically acts in all directions at a point. Basically, point a fluid, for example, it acts at all directions. You put a pressure sensor in the fluid, it doesn't matter at that point. It doesn't matter which direction your pressure sensor is facing. You always give the same reading. So here there's a more comprehensive explanation of why pressure is a scalar quantity. So let's say you have a gas, and let's say you have a uniform gas that doesn't move. So uh, you walls in the gas to form a container, and inside that container, the force per area or pressure will be the same since it's a uniform gas. So you can keep shrinking the size of the container down to an infinitely small point, and the pressure will have a single value at that point. So what this means is that pressure has a magnitude, no direction, so it's a scalar quantity, not a vector quantity. Okay, yeah. So now let's say you have a container filled with a certain fluid. You want to find the pressure acting at the bottom of the container. Okay, so we want to find the pressure acting on the bottom of the container. So the first thing, so wait, let me. Okay, so the first thing you need to know is that P equals FA. So here F is basically the weight of the fluid, or mg. So here we define m to be the mass of the fluid and g to be the speed of gravity over a. Then yeah, so here basically so now let's define. So you know that. So let's introduce density, which is the Greek letter rho. So density is defined as mass over volume. Volume. Okay. So you know mass is basically rho v. Okay. So so we continue deriving. We you have uh, P pressure equals um, P P wait, P rho v over A. Here you must note that what is V over A? V over A is the volume of the water over the base area of the container. So this is a cylinder, right? You will know. So define the height of the water or fluid to be h. H. Okay, so this is h. Okay, so this is h. So you have P equals P rho h. Yeah, so this is basically the formula for pressure in a fluid. Pressure at any point in a fluid. So mm, so yeah, okay. So basically, once you know the density of the fluid and the height of the fluid, you can calculate the the pressure at a certain point. Say like you want to know a pressure at this point, you must you must know the height. You must know the height between height this point is below the water level or whatever fluid level, and you need to know the density of the fluid. Then you can calculate the pressure at this point. Okay, yeah. So oh, okay. So wait, let me move this here. Okay, yeah. So let me move this here. And the definitions and erase everything else. So time is a mass. P is the speed of acceleration of gravity. Rho or small letter p, which I'll put here. It looks like a lot small letter p is the density. V is the volume. And what else? Yeah, that's it. Oh wait, no. It is the height. This is the formula for pressure at the point in a fluid. let me reset it. Okay, so one thing you need to know is that pressure um, pressure does not oh gosh pressure does not depend on the shape on the of the container, only the height of the fluid. So let me draw two examples to illustrate. Here, so you have a container filled with fluid here, and here you have let's say a funnel. Yeah, filled with water until the same level. Uh, so it's the same level. Okay. So the thing is, this is Pascal's second law. Basically that um, pressure at let's say here and the pressure at here is the same, even though the shape of the containers are different, assuming the height is the same. So the pressure at the bottom of the container here is equal to the pressure at the bottom of the container here, even though even though um the, even though the volume of the water and the shape of the container is different. So this is actually contrary to what we may think. Like most of us may think that at the bottom of the pressure here may be more than the pressure here, may be different from the pressure here because of the shape of the container. It's of the shape of the container. Like here's a bit more water here, the side here, or simply because this is a bigger base area. So let me explain why pressure has only depends on uh on the height. So wait, before that let me explain something else. So pressure as a scalar acts on all in all directions at any given point. So let's say at this point you poke a hole, the water will squirt out, let's say in this distance away from the container. If you poke a hole here, it'll squirt out further because the pressure at this point is greater, because P equals H rho G. Here you because P and H are because given the fixed fluid, density and the gravity won't change. So P, the pressure will be directly proportional to the height of the fluid at which you put the point. Okay, so here you can see. So by right, this is supposed to happen. Yeah. Okay, so now I'll explain why pressure doesn't depend on the shape or size of the container. Yeah.
Here we have a cylindrical, straight-walled tube filled with water, and next to it we have a funnel filled to the same height, clearly containing more water. We see here that the weight of this water in the first tube is balanced by 50 grams on the other side of the scale, as expected. Now, let's see how much mass is required to balance the water in the funnel. 50 grams, the same as a straight-walled tube. But wait, if the vessel contains 630 grams of water, but only 50 grams are required to support the water, what is supporting the rest of the water? To solve this apparent conundrum, we need to understand one more thing about pressure inside fluids like liquids and gases. In our first example, Giselle's weight is acting in the downward direction, and thus she exerts a pressure against the floor, but not against the wall or the ceiling. But take a look at this. I'm filling this enclosed container with smoke by pulling up on the piston. Notice how when I push downwards on the piston, the smoke flows horizontally into this spherical glass bulb. If I continue pushing straight down, the smoke escapes out of all the holes in the glass, not just the ones on the bottom, but even the ones on the side and on the top. This means that the smoke is pushing against all surfaces in the container, including the walls and the ceiling. If I increase the pressure by pushing down harder, the smoke escapes faster in all directions, which means that the pressure increases everywhere inside the gas. This is Pascal's first law, that if the pressure at one point in an enclosed fluid increases, the pressure throughout the entire fluid also increases, and the fluid pushes in all directions. Although we have demonstrated this with a gas, you can imagine that the same thing would happen if we fill the container with water, or anything else that flows. Now let's go back to our funnel and see if we can shed light on our conundrum. Now we know that if we poke holes in the sides of the funnel, water will squirt out diagonally down, which means the water is pushing on the funnel in that direction. But since there is no hole, the funnel wall is preventing the water from flowing out by pushing back against it in the opposite direction. So we see that even though the funnel wall is slanted, it pushes up, as well as sideways, against the water. And this is precisely the extra support that we were looking for. So it turns out that the walls of the funnel are supporting the extra water, and the stopper at the bottom is only supporting the column of water directly above it. Let's try to use this idea to explain what happens with a third glass vessel here. When filled to the same height, it contains much less water than either of the first two. And yet, when we measure the weight required to support the water, we see that it also takes 50 grams. Namely, the force required to support the water is greater than the actual weight of the water. Where is that additional downwards force coming from? Well, let's remember to apply Pascal's first law. The glass vessel contains a horizontal sealing part to it. If we poked holes in it, the water would squirt up, which means the water is pushing up against this part of the vessel, and thus the vessel is actually pushing down on the water, causing the stopper to support more than just the weight of the water. Now I pose a challenge to you. Here is a slanted tube filled to the same height with water. Notice how most of the water is not directly above the stopper. And yet it also requires 50 grams to balance the pressure at the bottom. Why do you think that is? I'll leave that as a puzzle for you to figure out. This experiment is similar to the one Pascal did when discovering his laws.
Okay, so basically, that is the explanation for Pascal's second law, which is pressure does not depend on the shape or size of the container. So let me go into further detail. So for the third container she used, okay, fine. Yeah, so here's the third container she used. Okay. The third container she used, and it is filled with water to, say, this water level. So let me zoom in a bit. Yeah, so here, here the height, here the water exerts a pressure in, let's say you actually let's say along this area the water exerts a pressure on this ceiling part upward. Okay, so let's say you, at this point with an infinitely small area, it exerts this much force due to the pressure. So the ceiling of the container will exert a pressure downward. It will exert a force downwards in the same direction because of Newton's third law. With the same area, it will thus exert the same pressure that the water exerts on the ceiling. So basically, because pressure is a scalar, the pressure can also act downwards in the direction of whatever you are weighing the container. So this is yeah. So this is sort of like mm, okay wait yeah. So the thing is, how much pressure is the water acting on the ceiling of the container? So previously we know that this is um, that define the height at this point from the water level to be h. So we know that the pressure at the point that the water is acting at the ceiling at this point is h rho g. So h rho g is the ceiling is acting a pressure of h rho g on the water also. This is basically like at this point you have a certain amount of water at this level. This is true for all the points here. So basically it's like having extra um, an extra level of water and extra like sort of like it's sort of like having an extra cylinder shape of water above here where the water acting down where the water acting down is the pressure of the water acting down at this area is the same as the pressure the vessel acts on the water here. So overall the the, the pressure of total pressure of that is acting on the base area of this container is similar to if the container was simply a cylindrical vessel. Okay, so um, wait, what? Okay, so now let me explain the challenge she gave. So okay, so here is the okay, let me draw this back. Here is the shape of the container. Yeah, and let's say it's filled with the same height as the one on the left. So let's zoom in and let us take note of this point. Take note of this point. Okay. So along the area, pick a point with a point with the so let's say I pick this point. So the water exerts a pressure and multiplied by the very small area, you get a certain force. So you get a certain force. Okay, you get a certain force. By Newton's third law, the vessel will also exert the same amount of force on the water. So find the height at this point to be h. Yeah, okay, so pressure, the water acts on the wall is h rho g, so the pressure, because force and area is the same, the pressure that the ceiling acts on the water is also the same, which is h rho g. To do this for all the points, along this area, you get a cylinder-like shape. It's like you have an extra cylinder of water above here that's giving the pressure. So yeah, so yeah, so this is of course already similar to the if this container was a cylinder instead of having this slanted top. So and from there we already know how to calculate the area or the pressure at the base, which is h rho g. So this is Pascal's second law. Okay. Um, okay, so now I'll explain the piston systems. Pistons. So piston, yeah. Please wait for a while. Okay, yeah. So assume that here this is filled with water. Okay, so let's say you exert uh let me zoom in. Okay, so let's say you exert force of F1 of F1 here. Let the area of the piston here be A1. Okay, so here the pressure is equal to F1 over A1. So note that the pressure throughout the water must remain the same. Okay, because yeah, because this is a liquid, liquids cannot be compressed, so the pressure throughout the water must remain the same. So here the area be A2, where yeah, and because P equals, so let the force exerted here be F2. So because here, because you know F P equals FOA, you can also say F equals PA. So we have F2 equals A2 P. Here you may notice something. The pressure is the same. Wait, let me write this here. So the pressure is the same, and here A1, A2 is much larger than A1. So what this means is that F2, the force exerted here, is much larger than F1, the force you exert. So this piston system is very, so you can use this piston system is very effective at multiplying forces. So you can say exert a force of only 10 newtons here. If you make the area of this piston large enough and make the area of this small enough, you can even lift the very heavy weights of like let's say 1,000 newtons. Yeah. So basically, you can use this formula know that F2 over F1 equals A2 over A1. Basically, you can use this and figure out that how much, when you exert a force here, how much would the resultant force be over here. Okay. Yeah. So let's zoom in a little further. God damn it. So wait, let me remove this here. So let us examine the let us examine what goes on each side. So let's say you push the piston down by a distance of d1. So after a while, the piston, the fluid, so after a while the fluid will be at this level. Yeah. However, you must note that since liquids cannot be compressed, the volume of water must remain the same. So here, here you know the volume is equal to A1 of A1 D1, base area times the height. That means the volume on the other side, the rise of the volume increase on the other side must also be the same, V. So yeah, so you know V V V equals A2 D2. Here D2 is the area that the piston rises. Okay, so after a while, this So after a while, you push the, so this will rise by distance of d2 when you push the piston on the other side down by the distance of d1. Okay, so but here note that since the volume is the same, the A2 is much bigger than A1. So here, since V is the same and A2 is much bigger than A1, this means D2 is much bigger than D1. D1. Okay. What this means is that although you exert a much larger force on this piston, the distance you move it up by will be much smaller than the distance you push it down. If yeah, okay. So yeah. So basically this is how piston systems work. And something to note, right, is that although the force you exert here is much larger than the force you exert here is much larger than the force you exert, because the distance is much smaller on the other side, just find the work done. The work done will actually be the same. The work done is basically F1 D1 on this side is equal to F1 D1 times A1 D1, which is equal to PV, the pressure times the volume. Then here you use the equations. This is equal to F2 times A2 D2, which is equal to F2 D2 equals to W2. So okay, I'll define this as W1. So basically the point I'm trying to make here is that although the force here is larger than the force here, because the distance here is much smaller than the distance here, essentially you're not actually saving any energy when you have a much larger piston area here. So yeah, you can actually make the piston here larger than the piston here to, if you want to lift here a lot, very high, but most of the time we see A2 being larger than A1. Okay, okay, yeah. This is okay. So the last, yeah, actually wait, I think I should. Okay, yeah, never mind. So the last thing I'll be talking about is how barometers and manometers work. Okay. Okay. Yeah. So first I'll explain how barometer works. Barometers is basically like you have, let's say, a basin of water. Yeah. So you have a basin of water and a test tube of water with a stopper below. Yeah. So here's the stopper. And it's filled all the way with water here also. Okay. So how a barometer is used to measure um, atmospheric pressure. So basically you insert this thing into here. Yeah. And you remove the stopper. So here the water level is, yeah, here the water level will go down. And here the water level will rise. Mhm. Okay. Yeah. So, and essentially here you actually create a vacuum because air can't enter here. So, so right, this is an instrument used to measure atmospheric pressure. Why is this so? So basically here you can use HOG. So the atmosphere exerts a pressure. Wait, yeah, the atmosphere exerts a pressure here. Okay? And here, and this is, yeah, and this is what prevents the water from going down further. Here you can essentially use this to measure HOG to measure the atmospheric pressure. Okay, so here, let's say you have a height H. Yeah, so you know the density of the fluid. Hmm. Okay, fine. So here, um, the pressure exerted. So let me go off and uh, explain. Let me go off and explain something else first. Oh wait, never mind. What am I doing? Okay, fine. So wait, the thing is right. What am I doing? I'll use black. This water level, right? The pressure here, the pressure exerted is supposed to be the same. Okay, the pressure here is similar to the pressure at here. Okay, so the thing is here, what is being exerted is atmospheric pressure. Atmospheric pressure. And here, what is being, since there's a vacuum here, the only pressure that's being exerted is a column of water here. So, yeah, so define this to be, actually, yeah, so define this to be H, and actually, you know the pressure here exerted by the column of water is HOG. Wait, yeah, I'll just show this here. So the pressure exerted is HOG. So that means at the pressure of the pressure being exerted by the atmosphere is HOG also. HOG, yeah, yeah. So that means the pressure being exerted by the atmosphere is HOG. So with that, you can calculate the atmospheric pressure. Okay, so in fact, the higher you so atmospheric pressure or P ATM is equal to 101,325 Pascals. Okay. Yeah, so this is also, you can basically say this is actually 1 ATM. And the thing is, right, let's say you bring this barometer up into a mountain, the water level will go down even further because the pressure has decreased. Okay, yeah. And before I go on to explain manometers, um, I'll explain something else first. Okay, right? Yeah, so here is a column of water. Here's a column of water, okay? And let's say you have a pressure sensor here. Basically, you put this pressure sensor at point of the liquid to measure the pressure. So if it's here, the pressure measured will be H rho G. Depending on how deep you go, the pressure will keep increasing or decreasing proportionally to how the height increases or decreases. Basically, P is directly proportional to H because rho and G is fixed. So what this means is that move this up here because there's no depth, the pressure measured will actually be 0. Then you may ask, what about atmospheric pressure? Doesn't it exert the pressure on the water as well? So here I'll explain absolute pressure and gauge pressure. So most of the time when we talk about pressure, we talk about gauge pressure. So for example, the 0 over here is the gauge pressure. It's the gauge pressure at this water level. In fact, the absolute pressure. Let me see. Okay. Yeah. So this is the absolute pressure. Absolute pressure is basically defined as the gauge pressure plus the atmospheric pressure. Alright, this atmospheric pressure varies as you go up and down as your altitude increases or decreases, but most of the time it stays around the same level. In fact, it most stays around the same level. So the gauge pressure, so this 0 here is basically the gauge pressure. The absolute pressure is the gauge pressure plus the atmospheric pressure. Okay, so the absolute pressure here in fact is water is your 101,325 pascals plus pascals plus whatever plus whatever reading is here. Right here, absolute pressure is 101325 pascals. Then to move this gauge pressure down throughout the water, absolute pressure becomes the atmospheric pressure plus whatever reading is measured here. So why do we normally use gauge pressure instead of absolute pressure, since this is technically more correct? It's more for practical reasons. Basically, it's more for practical reasons. Let's say I have a deflated balloon, okay, and would you rather hear me saying the absolute pressure of the balloon is 101325 pascals, or do you rather hear me say the gauge pressure is 0 pascals? I think most of you will want to hear me say the second one, since it's simpler. Most of the time when we talk about pressure, we normally subtract the atmospheric pressure from it to make our lives easier. Okay. One thing to note is that atmospheric pressure is due to air molecules acting. Okay, so here the air molecules are actually pushing down the water, so which increases the pressure actually quite substantially. Okay, yeah. So assuming there's no atmospheric pressure at all, water would just float, float. You know, assuming there's gravity, no atmosphere, water level will actually be probably be much higher. Don't know, but basically the pressure would be absolute pressure would be much lower. Okay, because when there's no atmosphere. The thing here to note is that here it's a vacuum, so there's no atmospheric pressure acting. The absolute pressure here is actually just H rho g. Okay, here there's atmospheric pressure acting, so here it's not absolute pressure. At this point, the absolute pressure and the gauge pressure is supposedly the same because there's a vacuum here, so no atmospheric pressure is acting. But here there's atmospheric pressure, so just take that into account. Okay. So now I'll explain manometers. Okay. Okay. So manometers are basically a U-shaped tube. I'll draw it. Okay, zoom in more. Please wait for a while. Okay, it's quite badly drawn, but you get the idea. So, okay. So manometer is how manometers work. Here you have one. Manometers are basically a U-shaped tube. So on one side, an open end for air or whatever things to go in, and here you have basically here, which is the liquid you use to measure. Wait, I'll label things. Here is basically uh, a vacuum. Okay, so this doesn't affect the pressure at all. So here, here we have a liquid with known density. Okay, so this is normally water or mercury. Most of the time, actually, mercury. So on the other side, so manometers can be used to measure the densities of either air. I mean, yeah, the densities of either air or water, air or liquid, gases or liquid, by the pressure it is acting on it on the manometer. So basically here will be basically gas or liquid. Okay. Okay. So let's assume that. So here let's just assume that that there's a certain liquid. Okay. So first you find the pressure that the liquid is exerting. Just assume that this blue fluid is water. So to find the pressure that red liquid is exerting on water, you 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 use H rho G basically. Okay, then you measure the height. You measure the height H. Measure the height H. Okay, then here and okay. So here by right there should be a vacuum here so that atmospheric pressure doesn't affect the reading, I think. So let's just close this. So 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 you know the pressure here. So the pressure here acting acted. Right? So okay, this water level, the pressure you measure, if you place a pressure sensor here, will be H rho G. You can calculate because you know the density of this liquid or water. Then here, you don't know the pressure. You can, since the pressure must be the same, or the water level will go up or down. The pressure here must be the same. So you know the pressure here. So also here, you know the other height. So you know the other height. I'll just label it H2. So basically, so you know P equals H rho G. You know P, you know H, but you don't know rho, but you know P. So you can use this, you can calculate the density of this liquid. Okay. So basically, so so basically H1 rho 1 G equals H2 rho 2 G. So you know this is, you know rho 1 H1, you know G, but you can actually cancel it. So you know H2, so you can calculate the pressure. So you can calculate the density here, rho 2. So what if, let me see. Okay, yeah. What if, let's say, there is atmospheric pressure here? It's not, you can still do the calculations, but you need to take into account that there is a plus P ATM here. Yeah. So here at this level, only there's the volume of the red liquid acting here. There's atmospheric pressure also acting. In fact, right, most of the time in barometers and manometers, we don't use water, because water, we use mercury instead of water, because mercury is much denser than water. The height required is going to be much less. So P PATM, right, is not only equal, you don't need you don't actually need to 101325 pascals. It's not the only way you can represent atmospheric pressure. You can also represent it as 760.0 m m Hg. What does this mean? Wait, first let me explain pascals. Oh wait, let me just point out something I forgot to point out just now. Pascals is basically newtons per meter square, because SI unit equals FA. SI units, F is N. Actually, technically not SI. But normally F we use N. A we use meter square because meter is the SI unit. So P is in pascals is newtons per meter square. So what does 760 mmHg mean? It basically means that like let's say it's basically the pressure exerted by 760 millimeters height of mercury. It's like here, wait, we have mercury, and here here is atmospheric pressure. Okay, so what 760 mmHg means, right, is that this height is 760.0.0 mm. Yeah, so basically the pressure here is supposed to be equal to the pressure here. So the pressure here is atmospheric pressure. The pressure here is the same, which is 760 millimeters of mercury. This is basically what 760 is. So this is another way to measure to measure atmospheric pressure. Okay, so why is this so, right? So I'll try and derive this. Wait. So basically we are using P equals H rho G again. And here note that this is atmospheric pressure, which is this. So wait, the density of mercury is wait, please wait. Alright, sorry. How long is this? Ah, oh god. Oh god. Sorry, please wait. Okay. So this is I'll use SI unit. The 13593 kg wait per meter cube. Okay, so most of the time we just know it as 13.6 grams per cm cube. I think, yeah. Basically, you know this, right? So we can calculate H, which is 10. Yeah. Yeah, so this is 1013.5 times 13.5.3 times, I'll use 9.8, 9.81 to be more exact. Then you can use your calculator. Find this is you will get 0.75. Oh, wait. You get 0.759. I'll just add one more. That's on page 8. Yeah, so you get this. And this is in meters. So when you convert it to millimeters, you get basically when you convert this to millimeters, you should get this value. Okay, and this is pressure. So I'm done. Okay, actually wait. Yeah. Why did I do this? Oh my god. Okay, anyway, the next topic is moment. Okay, sorry. Wait, sorry for wait. Okay, fine. So when we here, now I'll talk about moment. Um, hmm, Okay, so first let me start with the definition of moment. Okay, so here, let's say you have an axle rotating about a pivot. So here is a pivot. Okay. Um. Yeah. So let's say you apply a force here, at the distance d away from the pivot. So the moment, or simply put as m, is defined as force times the distance it is away from here. So assume this is a right angle. Moment, yeah. So basically, moment is defined as the force times the perpendicular distance uh, from the pivot to the force. Okay. Let's say you have a slant. Well, use this line. Let's say you have a slanted force here. So this is use F2 here. Here, basically, E2 will be distance here. So this is D2. Okay. Yeah. So here, anti-clockwise moment will be FD. I'll just put this. The anti-clockwise, I mean the clockwise moment will be F2 D2. Okay. Yeah. So yeah. So one thing to note is that if let's say there's like another force here at the second and distance away from the pivot, the moment the clockwise moment is actually the sum of all the forces in all the forces times distances pointing in the anti-clockwise direction. Okay. Yeah. So it's basically the sum of all the moments of each individual force. Okay. So I'll just put this here where so here m is the moment, f is the force, and b is the distance. So actually, right, moment can also be moment is also the name, also defined as the torque. This is another way of giving the same definition. Okay. So what the law of moment says is that, okay, so now the main part. What the law of moment says is that is that if system is balanced, then m AC, which is the sum of all the anti-clockwise moments, is equal to mc, the sum of all the clockwise moments. Okay, so basically I'll use the sigma sign. Okay, sigma sign basically means summation. So summation of all the anti-clockwise moments in their respective distances. I'll just put it like this. Is equal to the sum of all the clockwise forces and their distances. I'll put it this way. Okay. Yeah. So now let me explain why this is true. You prove it basically. Okay. So let's say here. Okay. You know what? Here. Okay. So let's say here you have a force here. F. Actually, wait. Okay. So let's define. So at the point where the force is being pulled, you let this draw the. So we draw the line such that this is a right angle. Okay. So this and this is the distance. Okay. So in fact, the proof, right? You actually need a bit of knowledge of rotational kinematics. Yeah. So let's define this distance as r, the point where the force is being pulled on the pivot from the pivot. Okay. The let me see. Okay, yeah. Define this theta 1 and define this as theta 2. You know that this is also theta 1 because yeah, for this definition theta 1 plus theta 2 equals 90 degrees. Okay. So by the definition of a moment, m is defined as Fd. And using our trigo, this is equal to that E is actually equal to R cosine theta 1. Yeah. So this is, so we move the R outside. This is equal to R F cosine theta 1. Put brackets here. So now we'll do some resolution of forces. Okay, here's F. So if you don't understand resolution of forces, you can go forward in the video and watch that part first before coming back. So this is F, and now I'll resolve this into the two components. I'll use a different color. Yeah, I'll use. Okay, let me use blue. So I'll resolve it into two components. One is perpendicular to R, the other is parallel to R. Okay. So in fact, wait, let's just oh god, never mind. So anyway, that's the magnitude of this force is F sine theta 1. This is F cosine theta 1. Okay, so this F sine theta 1 F fine, forget it. So basically you can move this force here and this will not affect. The thing is, right, this is the component of the force that will affect the rotation of the around the pivot. This F sine theta 1 is the force pointing inwards towards the pivot. So this force will basically not affect the rotation at all. This is the component of the force that will affect the rotation. Note that even when F is perpendicular to R, the R, right, this holds true. So yeah, so this is how moment is defined. So now is when the part about rotational kinematics comes in. The thing about moments, right, is that the thing about moments is that I'll use torque. So torque, right, the torque is normally used by the represented as the Greek symbol tau. And the thing about torque, right, is that it is proportional to something called angular acceleration. Okay, I'll explain. So you probably know about in kinematics already about displacement, about displacement, velocity, displacement, velocity, and acceleration, normally represented by these three letters. So most of the time, these are linear. These are all linear. Most of the time, we know them as linear quantities. So displacement in a line, velocity in a certain direction in one line, and acceleration also linear in one line. However, there are angular quantities as well. Angular quantities is basically, let's say, angular displacement, which means like when an object rotates around a pivot, the distance it has rotated, let's say like it has rotated 300 degrees. But normally we use when we talk about angular quantities, we use radians. So like this can be 5 over 6 times 2 pi, which is 5 over 3 pi. Okay, so angular quantities we use theta represent. So for velocity, I think you can get the idea already. So velocity, right, basically how fast the thing rotates per second in terms of radians. So let's say like 2 pi per second means object completes one complete revolution per second. Pi per second means a half revolution per second. So it's normally represented by a Greek letter omega. Then acceleration is basically the change of velocity with the change in time. So like pi per second square, pi over 6 per second square, this sort of quantities. It's represented by Greek letter alpha. Okay. So the thing right is that the moment is, is that the moment or torque is directly proportional to um alpha or angular acceleration. And if you want to know more about rotational kinematics, you can watch my video which I posted. We can watch my video on rotational kinematics. So it will explain more in depth. So as for why this is true, I don't exactly have a proof, but in rotational kinematics, it says that T is equal to IA, where I is something called moment of inertia. So when the whole system is not moving, what this means is that the angular acceleration, the clockwise direction, is equal to the angular acceleration in the anti-clockwise direction. Okay. So what this means is that the moment in the clockwise direction will be proportional to the moment in the anti-clockwise direction. Moments is basically your torque, the sum of all your torque, which is by right this quantity. So I don't exactly have a proof for this because I couldn't find a proof of why this is true. Because if I can find a proof of this, then we are done. So, but for now, just take it as it is, that this is true. Actually, this is more or less just Actually, this is just more or less what you need to know about moment. I'm just going to give tell you a couple more things. Okay, the first is that you must recognize where the pivot is. So the thing is, right, sometimes question can give you such that the forces are acting on like opposite sides of a pivot, like here and here. Sometimes they can give it to you such that they're acting on the same side. For example, like this, and like this. Yeah. So you must be able to recognize where the pivot is to know where the distances are. Okay. So there are only two forces in the picture, like let's say most of the time there will only be two forces. If there are more, you just add them up. So in this case, in this anti-clockwise direction, you have F1, you have D1, you have, and here you have F2, D2, D2. You know that F1, D1 equals F2, D2. Okay. In fact, I think I should move this here. And the second thing, yeah, the second thing is to note is that it doesn't matter how the axle looks like. So for example, your force could be, the pivot could be here, the force is in this direction, the axle is like some weird curvy thing, some weird thing that looks like this. The thing to this looks like this. Okay, here's the force. The thing to note is that here, the thing to note, you only need to note of the thing to note here is that you only need to take note of the direction of the force, like here. If you want to know what R is, as in the previous example, R is here. But what is most important is the direction of the force. So the perpendicular distance, right, is basically here. And this is what you use to calculate your moment. Okay. Yeah. So now I'll talk about uh, resolution of forces. Yeah, okay. So now I'll talk about resolution of forces, which I actually realized I talked a bit about in one of my videos last year when I was talking about dynamic. Okay, yeah, so basically right. So I'll talk about vector addition first. You know that when you add vectors, you add it like this. You align them such that the arrowhead of one is the tail of the other, and this is the resultant. This is the resultant vector. Okay, so you probably so the thing you need about resolution of forces is that this vector, like when you have a vector, right, you can do the opposite of vector addition, like split it into two forces, like this, or like this, or you can even split it into like more forces if you want. Yeah, but most of the time when we talk about vector resolution of forces, we talk about splitting it into two, two, two. We talk about splitting it into two perpendicular components. Okay. Yeah. So then yeah. So you can resolve it into these two perpendicular forces, and you can like move this here, and basically the addition of these two forces will give this force. So basically, yeah, find this. Let's say you define this angle as theta. Okay, this is F. This is F. Then this, you can use your trigo. This is F cosine theta, and this is F sine theta. And this, and yeah, basically these will be the magnitude of the two forces. If you make it such that this is theta, this will be cosine F cosine theta. This will be F sine theta. Okay. Okay. So now let me go more into the applications. Let's say, wait, I need to use this. You have a ground, you have an object, and you are pulling a force in this direction, F, with the magnitude F. Okay. And if you want to, you're pulling it in, I use blue, pulling it in this direction. You're pulling it in this direction because the ground is this way. So how do you find, like, if you want to find the acceleration or the work done or whatever, how do you do it? So the answer is to resolve this force. So this is the direction that the force is actually moving, right? So the acceleration or work done or whatever is all in this direction. So we want to find the direction of the force such that this F this F such that this F direction. Okay, now I'll talk about more about it later. Yeah, so we'll basically resolve into these two perpendicular forces. This is F sine. Wait. This one. Yeah, F sine theta, F cosine theta, where this is theta. Then basically work done, your acceleration will basically be F cosine theta over m, because F equals m, you got the F in this case is F cosine theta. Then the work done will be F cosine theta times d, which is whatever distance you put it. Okay, now I'll talk why will you want to I'll talk about why you want to resolve it into two perpendicular forces. So let's say you have a force in this direction. You want to find that the effect of this force on in, like let's say this direction only. Then you can resolve it into two. Like I said before, you can resolve this force into two components. One that's parallel to the direction you want. Yeah, I'll just finish. Yeah, direction. So here's the direction you want. In this case, which is the horizontal direction. So you can resolve into two forces. One point parallel to the direction you want, and one perpendicular direction to the direction you want. And the thing about the vector that's perpendicular to the direction you want is that it is not affected by it will not affect this part of the vector. Like if like uh, so basically this will not have any effect on the component of the force that affect in the direction you want. That's all the things you need. This is basically the only component you need. Let's say like here, right? You want mm, you want want the component of the force acting in this direction, which is the horizontal component. So the horizontal component is well in so this is the component which is F cosine theta. So that's what you want. You don't care about F sine theta. Like you can even increase F sine theta to like some very high value with your force being like this, and your F cosine theta will still be the same. F cosine theta will, and your acceleration and work done will still be the same. Okay, but that's assuming there's no friction, because F sine theta, the vertical component, will affect your friction. Okay, yeah. So mm, okay, so I'll talk about a few more examples. So this is an example I used in my video, one of my videos last year. Yeah, it's basically where you have a box on a slope and you want to find the acceleration when it moves downward. And you know the weight of the force, which I'll put as mg. You know the angle of inclination, theta. Yeah. So assuming there's no friction, what is the direction, or what will be the acceleration of this down the slope? So the answer is to resolve forces. So you can do similar triangles. Actually, yeah. So basically, you have this is actually not really similar triangles, but because this is parallel to this, okay, and this is parallel to this. This angle, 90 degrees minus theta, will be the same as this angle, 90 degrees minus theta. This angle theta, this angle is going to be equal to this angle, this also theta, because you already know this is 90 degrees. So you put this as theta. Then you use your trigo. Wait, let me do something first. Yeah, this is mg. Then so this will be your mg mg sine theta, and this mg cosine theta. So this mg sine theta component is the component that you want to affect your acceleration downward. Okay. So if you want to find the acceleration, use F equals ma. So yeah. So in fact, yeah. So A is just mg sine theta over m, which is g sine theta. Yeah. Okay. So about mg cosine theta. Mg cos by Newton's third law, when the box exerts a force on this slope, the slope will also exert a similar force on this box. And this force is called the normal force, because it's like normal to the slope, which here normal means perpendicular. Probably you heard of this before, but just telling you again, this is called the normal force. Yeah, so basically this is how resolution of forces works. Wait. Okay. Yeah, so basically this is your resolution of forces. I'll not put any terms or equations here since I don't think they're needed. I'll move on to the last topic. Projectile motion. Okay. 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 Now finally projectile motion. Okay. Let's say you have a ball being launched here at an angle of theta to the horizontal. Okay, it's a very flat theta. Okay, yeah, and this, so this will be the path that the ball travels. Okay, so first, let me just have let you know that in projectile motion for our syllabus, that we don't take into account things like air resistance and things. The only force we take into account, external force, the only external force that we take into account is gravity. I'll put it here. So this is the only external force that we take note of. Here. So okay. Yeah. So I'll here's the ball at this position with the velocity factor being around here. Wait, I'll wait for me. Yeah. Okay. Okay. So excuse me while I draw these vectors. Oh my god. Yeah. Okay. So it's not exactly very accurate, but it will do. Okay, so projectile motion is basically just resolving the factors, resolving the factors into horizontal and vertical components and applying your kinematics. This is basically what projectile motion is. I'll zoom in and tell you the details. So yeah, so first I'll use red. Okay, so first, at this point, the ball is being launched to the floor, with being launched at certain velocity at this angle theta to the horizontal. Yeah. So we resolve into the horizontal and vertical component here and here. This is at launch. This is the horizontal component. This is the vertical component. And take note, I'll put this as V. This is V. Okay. Sorry. So this will be V. So at the start, this will be V sine theta. This will be V cos. Oh God, why? Cosine theta. Yeah, okay. Yeah, so this is the vertical components and the horizontal components at the start. What am I doing? Yeah. So now I'll move on to here. Okay, right. So take note. The only force that we are external force that we are considering is gravity. Gravity is acting in the vertical direction. So the horizontal component is not affected all the way through the motion. The vertical component is. So because gravity is an downward acceleration of 10 meters per second square. So basically when this vertical component is pointing outward, the vertical velocity will keep decreasing, decreasing, and getting shorter until it reaches 0 at the maximum height. Then the velocity vector will keep pointing downward, will point downward and keep getting longer until the ball lands. Yeah. I'll draw all the yeah. So this is still your wait, let me finish this first. This is actually still your V cosine theta from the start because it hasn't been changed by the gravity. But this is actually shorter already. So the magnitude of this force is basically V sine theta. And this at maximum height, there is no vertical component. The horizontal, yeah, it's only a horizontal component. And the magnitude of this velocity is VA cosine theta from earlier. And here the velocity starts to go downward, but yeah, take note take note, right? Here the magnitude of the vertical velocity is still less than v sine theta, because basically at the same I'll expand. Basically when the ball is launched and at the same elevation, when it reaches the same elevation as when the ball is launched, that because we are discounting air resistance and stuff, that will be when the v magnitude of the downward velocity reaches v sine theta again. So yeah, so this is so here your vertical velocity is still less than v sine theta. Then here, assume that it's the same elevation as when it was launched. Oh god. Okay, alright. Okay, I'll draw what it's supposed to be, right? Yeah, right, the v cosine theta velocity vector is supposed to remain the same all the way. But apparently I forgot to make it longer. This is supposed to be like this, and this is I'll draw the new erase this and draw the new force. This is what the force is supposed to be like. And yeah. V cosine theta. V cosine theta. V sine theta. Yeah. Now, try and recall your kinematics formulas. I'll write them here. So, wait, I'll use text box. Yeah. Okay, the first one is V equals Q plus AT. The second one is V square equals U square, I'll put the square later, plus 2AS. Third one is S equals half U plus VT. Last one is S equals UV plus half AT square. I'll put a square. Okay. Put this here for now. And the thing is, right, in projectile motion, basically you are using all these equations, but in the vertical and the horizontal component direction. Yeah. So let's say, so now let us so now I'll take you through how to use these equations. Now let's say you want to find the max. Okay, so let's give v a value. Give v give v a value, v and theta a value. So v equals 10 meter per second. Theta equals 30 degrees. Okay, I'll just put 30. Yeah. Okay. So here v horizontal component is v at the start. The horizontal component is v cosine theta equals 5. Yeah, 5 square root 3. Use your trigo. Then your v sine theta your v sine theta is 5. Okay, I'll zoom in. Yeah. So now let's try and find the maximum height. So one thing to note is that what's this? One thing to note is that at maximum height, the vertical velocity equals 0. Yeah. So yeah, vertical velocity equals 0. And so basically you know v, the vertical velocity at the start, and the vertical velocity at the maximum height, and you know the acceleration. So I'll do this here. V subscript v. We use v equals uat. V subscript v for v vertical equals u subscript v, the vertical whatever, plus a v t. So these are in the vertical components. So depending on what you define to be the positive direction, you define v and u as such. So assuming the upward direction is positive, we have 0 because the v here is 0, the vertical component is 0, equals 5. I'm not going to care about sig fig and stuff for now. So 5 because here is 5 because here u is 5 plus minus 10 because acceleration of gravity t. Using that you can solve for t. Yeah, okay. T equals -5 over equals to, half. So in half a second, the ball reaches maximum height. Okay, so now next question. What is the maximum height reached? Here, so what is the maximum height reached? So here what you're finding is the vertical displacement. So we can use, we know, um, we know U, we know V, we know T, but we don't know S, so we can use S equals half UV plus T. So vertical displacement equals half U vertical initial velocity plus final vertical velocity times the time. I think you have already found the time. You have already found the time here, which is half. So equals half, and this is 5, this is 0, half. I'll just put them here. So half times 5 times half. Yeah, equals 1.25 meters. Again, I'm not going to care about sig fig for now because I'm a bit exhausted and just take note when you're doing the working. Yeah. So yes. So that means I'll draw it here. Yeah. So this is 1.25 meters. Okay. So now now let's find what is the horizontal displacement, like when it lands, how far it is from when it is launched. So it's basically this distance, and here we are assuming that the that the elevation at which it is launched and the elevation at which it has landed is the same. Okay, so and because of because of this we have symmetry. So it takes, from our calculations, it takes 0.5 seconds for the ball to reach maximum height. So by symmetry it takes 0.5 seconds to land again. So total time taken is 1 second, as you can see. So now we calculate in terms of the horizontal component. So S equals, I'll just write it here again. Yeah, so we will just copy here again. As you have to see. So T is basically 2 times 0.5, which is 1. And here you note that U and V are both the horizontal components, V cosine theta, which has stayed constant throughout the whole journey. So basically, so both of them are 5 square root 3. In fact, you can just for the actually we are out. I forgot. Yeah, this is the horizontal displacement velocity. So basically, what we can instead of you can just reduce this to saying S horizontal S equals vertical. Horizontal velocity times the time, which is equal to 5 square root 3. I'm not going to use calculator. So 5 square root 3 plus 1 equals 5 square root 3. Yeah. And one last thing to know. What if you want to calculate the velocity at a certain point in the trip let's say like here, you know the horizontal velocity, you know the vertical velocity, but you want to calculate the total velocity, which is like in this direction. So you just here basically you just use your Pythagoras theorem after finding VH and VB. So V equals VH square, which stays constant all the way, plus VV square. Yeah. So this is your Pythagoras theorem. This is about So this is about all you need to know. So this is about all you need to know for projectile motion. Wait. So the main thing about projectile motion is not really the equations. Equations are just kinetics equations which you have learned before. The main thing is the application in both the vertical and the horizontal direction. So sometimes the question can give you can be such like, oh, a car drives off the cliff. What is the landing velocity or something like that? Then basically all you need to consider is this portion. Wait, lagging. All you need to consider is this portion. You don't need to care about like the starting part. At the launch it already is at like maximum height. Same for like if you're trying to throw a ball onto a cliff, a higher elevation, then you're just considering this part. Or it could be like the landing elevation is different from the starting elevation. In this case, just consider the starting part and the starting half as the part before maximum height and the part after maximum height separately. So I think that's all for this video, and I hope you found it useful, and thanks for watching, and bye.